Hi, my name's Bob Grenier and I'm a volunteer with the Martin Fleischmann Memorial Project. So thank you for joining me this evening. I hope the audio is working fine. If everyone or anyone can give me a hint as to whether you can hear me and see me okay, that would be great. I have something to show you tonight that I worked with C.I.C in Brno yesterday with their lovely scanning electron microscope and EDS on the Vega Valley. In fact, I looked at two samples, the Vega Valley and the actual aluminium sample that I ran in the, I think the 12 or 13 minute experiment description that I gave for how to do a ultra experiment. But we're going to do that another day because I think what I have to share with you today, I could not have imagined when I recorded what I recorded on a Saturday that on Monday, I would see what I saw in a coherent nuclear transmutation and ball lightning reactor. And it was the Vega Valley that we were studying again, and I could probably spend several months looking at that particular sample. But what I have to share with you tonight is, in context of what I've been talking about over the years, absolutely earth-shattering. And I just feel really honored. So thank you. Okay, so you can hear me. Great, excellent. Hi, Artifact. Hi, FPV Angel. Hi, Dan Moretti. Hi, Glass Chappie. Great to have you. I don't know how to say your name. Is it Drav Rajput? I don't know. Infidel, Apostate, and P900. Cool pics. So great to hear you. Hi, David Boutillier. And hi, Henk. Fantastic. So it's great. We've got a good quorum here. So I'm going to set up a couple of slides here. So if you just bear with me, I actually, this is going to be very, very, very raw because I just wanted to get it to you as fast as possible, especially in context of, you know, having talked about things on Saturday and having seen what I saw on Monday. Something in this universe is definitely working in our favor. Let's put it that way. Right. Okay. So give me a second and I will have something to show you. Right. So my machine always grinds to a complete halt when I pull one of these things out. And I will look at the images. So I hope everyone's okay today. Hi Jason, hi Louis, fantastic to have you, and the Signal, thank you. Hi TP Sven, and Bestoic Primer, wow, and Ambrosio Rossetti, and join the technicians. It's fantastic to have you all here. So I'll just wait a little bit longer to give another some chance for people to get in the room, because I don't think people are going to want to miss what I have to share with you tonight. And it almost seems too easy at this point. Anyway, I'm enjoying my work. Let's put it that way. Hi, Gordon. Great to have you here. And Corky. Well, we can start now. Corky's in the house. Okay, just give me a second. I've got one more thing that I would like to pull up. Okay, I think we can probably start looking at this. So, on April the 16th, I shared Ball Lightning and Coherent Nuclear Transmutation Part 1, and the video is here, you can go and review. But in the Ultra experiments, we observed the production, which is funny because we saw these magnetic structures, and that was David Boutelier when he replicated the experiment. And I suggested that this system would be producing crenellated magnetite or magnetic spheres. And so I asked Alan Goldwater, who originally inspired this experimental series, to run the experiment, which he did for a little period of time, and he picked out some balls, and guess what he ended up with? Exactly 100% what I predicted, and it just felt too easy. So we got these crenellated iron-rich spheres you can see here, and here's another example. And so this for me, and here's another example, this for me was 100% a sign that we are creating a coherent nuclear transmutation system. And the beauty of this is that my 5-year-old child can do the experiment, including learning and conducting the experiment, in 20 minutes. And so this is an experiment that can be run in very, very many environments across the world safely, and it only costs about $40 to get the materials up front, and then you can run the experiment with that equipment for many years. So it has a very small sunk cost, very small time investment, extremely easy to teach, and it produces these iron crenellated spheres. And so I had already seen these in a number of experiments, and I discussed this in the UFOs over Hessdalen, Norway, explained ball lightning and low energy nuclear reactions. And so I did a whole series of videos 3 years ago talking about this, and the fact that the tracks make kind of strange radiation tracks, and the fact that Dr. Graham Hubler of the formal Naval Research Laboratory, who said in 2000, or in 2001, early 2001, that they were very interested in the Abrahamson-Dennis model for ball lightning, and he went on to run the Skinner project at University of Missouri. And so that's that. And he's the person that proposed that what people are saying are EVOs are just Coulombic explosions. Yes, that's exactly what an ecton is. Anyway, and therefore it's nothing. And it's very interesting because that came across to me as another viewpoint, let's put it that way. But anyway, he had a lot of views to say, and the BBC decided at that time to interview him out of all the people in the entire universe about ball lightning. And it's just interesting that the Naval Research Laboratory came out with their high frequency gravity wave, or the Navy labs, or the US Navy came out with the high frequency gravity waves patent. Anyway, that's said and done. But I talked about various systems. But in the Hessdalen ball lightning, they observed where a ball lightning had crashed into the ground, and they dug through the soil sample of that, or the target where that was, and they found this iron-rich magnetic or crenellated sphere, which looks extremely like these iron-rich crenellated spheres that we are producing in our ultra experiments, it would seem, with very, very little effort. And we had seen these before, of course. We'd seen these in the NOVA experiment, which is a kind of ball lightning analog. And also we'd seen this sort of polar effect where something was being pulled into the pole. And we're going to talk about something similar tonight. And also teleporting from the inside of the core to the outside, there were these spheres. One of them is half in the Lion quartz. So in the reactor of Lion, if I go here, you have these cores here. On the outside you have some quartz, and on the outside of the quartz there were these highly magnetic spheres, and you can see a selection here, 3 of them, one that's half in and half out of the fused quartz, and there are these magnetic particles on crop circles, which I think is also quite interesting for a genuine crop circle to be having that. Anyway, so when I was talking the other day, I was talking, I mean, you can see there are different scales. So we've got one here, and it's this one is bound to this, and this one is bound to this. But I think the north-south predominantly on this runs along this pole, because you've got like a string of balls coming off here, and it's string of balls to this one. So, but these are a bigger scale to the ones that we observed in other systems. And also, this one was created in the system of Me 356. So this was in, I think this was tungsten and potassium carbonate discharge in water, and it ended up by producing this crenellated sphere, and it looked like it had a pole up here. So I thought this was all very interesting. So it wasn't much of a leap of faith to say that if we're getting transmutation in cavitation and we find that we're getting these magnetic particles being picked up, David Boutelier found that probably we would be finding these iron-rich crenellated spheres being synthesized, and it was just pure comedy when Alan ran his 360-second experiment and grabbed a few magnetic particles and threw them under the microscope and found iron-rich crenellated spheres. The other thing that I want to talk about is this triangles and spirals, which I referred to, and you can go and have a look at this video. And I've got some examples of in these various videos that I've shared over the years where I've observed these features, and they became a little bit obvious. This one is in the broken quartz of Lion. So you have these particular aspect triangles. The same aspect triangles were found in one of the Hutchison samples at the split plane. And then there's a softer one in aluminium, and this is much larger in one of our large aluminium samples from John Hutchison. And so I was saying, depending on the type of material, the event horizon of the monopole influence field will either produce a hard or a soft shape. So this is fused quartz, so it produces hard. This is iron, so it produces a hard with the event horizon. And in aluminium, it produces a soft fall off. And that you are going to get this vortex here, this Schauberger phi ratio spiral coming into the center if you're looking at it from top down. So you would imagine that this monopole structure is at the top here, and it's 50% through this structure. In this case, it is perpendicular from the structure, so it produces the vortex of the material going in. And the reason that the metal twists and breaks in Hutchison samples is that the monopoles, I described this in another video, where the monopoles, they build up, and they have a very discrete fall off in their field structure. And so if two monopoles of the same type build up, they don't affect at all. They get bigger and bigger and bigger, and when they fields interact, they just literally rip the material apart, and there's nothing at all that will stop it from shredding material. And so this is kind of my thinking on that. And it was in part because of this, but I just had this revelation, and it was, I think it was January the 8th, 2018, and I had a semi-conscious sleep state, and I came up with this thing, which I called the basic Yinno structure, which I shared actually for the first time in Sochi in 2018, in, I think it was October the 6th, 2018. So I kind of like, you know, when you have these kind of things in your sleep, you don't know whether you're kind of like completely making it up, you're actually realizing something. So the triangle is here. And the spiral is here also, and depending on whether it's I guess a north or south pole, it either goes in this way or it goes in the other way. Now I imagined something akin to a black hole here, and I described this in my Sochi presentation here, Seek and Share. Sorry, it was 4th of October 2018 to be precise, and I saw this as something akin to a black hole, but not a black hole. And I've later since said that this is probably something, well, it might be the ring that is alpha particles, or the core, but it tends to be that the lighter elements get made on the outside, and the core produces the heavy elements, but predominantly iron. And in fact, I did, maybe I can find it actually, what really is nuclear fuel. So this presentation, I think it's over 3.5 years ago. So I said basically, this is when I was coming up with the fact that, you know, Lena likes to make all the elements that are in the Earth's crust, and therefore the Earth's crust is a guide to the statistical likelihood of Lena synthesizing matter. And I talked about various things here, and I shared this graph, and this was a graph that was made by, I think it was George Miley, and at the time that it was made in 2009, I put red circles on all of the elements that were found to have been synthesized in labs, i.e. they were in the end material of the cold fusion, the LENA, or what I call coherent nuclear transmutation process. And of the labs, a number of labs reporting a transmutation to X in the 2009 Miley study, right? So there were, I don't know, there were 16 labs that participated in this May 2009 study. And the most of the labs reported the production of iron. Here you can see iron, okay? So 11 labs produced iron. And 8 copper, 7 calcium, chromium and zinc, then nickel and potassium, silver, chlorine, titanium, magnesium, manganese, cobalt, lead, and then aluminium, lithium, barium, osmium, carbon and silicon. Okay, but by far the majority of labs that were in this study in 2009 had produced iron out of their experiments, and I think that's important. And I think the form of this iron will probably be magnetic crenellated spheres. That's my gut feeling, or smashed up versions of the same. In addition, the MFMP up to March 2018 had observed these other elements being synthesized. But to be fair, if you included Adam and Co. and Leclerc with their respectively electrical discharges, relativistic speed electric discharges, and cavitation, you would have every element in the periodic table, including those well beyond uranium. Okay, so the process can synthesize it all, and the reason you don't see the noble gases up here and some of these, I think basically the gases are evolved, so you don't see them in the ash, and so that's basically why you don't observe them. And everyone discounts, or many people discount, carbon and oxygen because it's very difficult to not say it's some form of contamination. And also many people, when they are doing their analysis, they put it on carbon tape so they don't see things. They don't see the carbon because the carbon's everywhere on the carbon tape that they've got the sample on. But you can see that most of the things in the troughs you get synthesized, and I believe that that is because it's going into a small box. So that was that, and we saw some strange radiation there. So basically these crenellated spheres, and now about this particular structure, I found out that actually Alexander Shishkin had a similar kind of concept, and I think he borrowed it from another Russian, and he said that actually these solitons, these he called them string vortex solitons, they are the neutral form of magnetotoroelectrical radiation, which he said are effectively the same as EVOs, and since EVOs are ball lightning, then it's all the same thing. There's various scales, but he said that these things have a magnetic nucleus, and I think that's also true of Bogdanovich, where they say there is a magnetic nucleus, and electrons and matter are cohered down to that nucleus, and then you get this field coming off from the side. Anyway, so this is my basic structure that was shared first on October the 4th, 2018, and what I'm saying here is that there would be a magnetic core to this particular structure. Okay, with that said in mind, I'm going to start looking into some other data here. So just give me a second. Like I say, this is very, very raw, but you know, one of the guys at the university said, so when are you going to publish this? I said, oh, probably tomorrow. And they said, what? I said, yeah, I want to get it out the door. I don't have to think about it anymore. And he goes, but. And I said, well, I'm not trying to make money from it. I just want to get it out the door. People need to know. And so anyway, this is going to be very interesting. Okay. So I need to get up the actual analysis data, which is in here. Okay. It's not organized in any shape or form. I'm sorry. Okay. Oh, that really is a mess. Oops. Okay. I have to do this one at a time. No. What happened there? Okay. Okay. All right. Let's see. Let's see if we can do this one. Yeah. Okay. Okay, so first up on the Vega Valley, in one of the flat areas, we have a nice black Evo strike here. When I say black, it's black because it's black. Okay, so nothing other than I'm referring to the color here. And it seems to have deposited something on here, and by now you probably can all guess what that is likely to be, given what coherent nuclear transmutation likes to produce most of. And so let's have a look to see what we see. This is according to the data, and here it is, if I can get it here. So it's about 30 microns across. Am I going to be able to pan in there? Is it going to let me pan? Okay, there we go. So I've done a line scan, which I did across the diagonal, across this diagonal here. And one thing you can see is that, for instance, the zinc, because it's a brass plate, the zinc goes all the way down and then all the way up in the center and then all the way down and then all the way up. So across the dark areas here, the zinc is going down. And here you can see, guess what? The carbon comes from down between 0 and about 15. It goes all the way up to 80. So it's basically, if it's going from practically 1 to 80, that's a lot of orders of magnitude. It's nearly 2 orders of magnitude. And then it goes down a lot in the center, and then it goes up, and it's antiphase with the copper and with the zinc and with the sodium, which is likely synthesized here. And what else have we got? A bit of oxygen that goes down and up, and nitrogen's just flatlining at the bottom there. So there we go. We have a EVO, a rather nice EVO. Now, of course, this would not be a massively overdriven EVO because it's just synthesizing carbon, and this is not a spherical EVO. This is a toroidal EVO. And remember what the US military-funded research paper in fusion technology submitted in December 1993 said they are of 2 types, torus or sphere. And that's exactly what Matsumoto said in his work. And so here you are seeing a torus one, which is depositing. And I believe that as this deposited, it deposited effectively one coherent blob of carbon that settled down. And Matsumoto describes these as carbon films, and that might be what it is. It might be amorphous carbon, which we've seen in the work of Lyon, or it might be diamond, which is what was claimed by Leclerc is the most likely product to be formed. But in Matsumoto's work, I can show you here. He produced these carbon films. So if I change it to there, these are various carbon films that were produced and of various shapes and sizes. So that's what Matsumoto observed. Okay, so this, I just think this is a very nice example of an EVO strike of this kind. So now we're going to see something a lot more interesting. A lot more interesting. Okay. Now, some of these files are 16-bit and 8K by 8K, so they make my machine struggle a bit. But anyway, we will battle on. I'm going to try and kill a few applications as usual, because otherwise things may get tedious. You're going to love what you're going to see. You really are. Oh dear. I could have waited 4 days and just given you a short presentation, but my view is get it out the door. Get it out the door. Right. Let's hope this doesn't fall over. And we are going to go for... Okay, we'll do that one first. So, now at the end of the presentation, just after I got back from Italy, we observed this part of the Vega Valley where we saw the alternating bands of right and left polarized, circularly polarized material, or material that was circularly polarizing right and left light that was impinging on it. And we saw, and I've got this around the other orientation, something that I speculated may be an Evo, it might be dead, it might be alive, whatever, and that we might have a dark Evo. And so anyway, what we are looking at here is this same thing, but it's actually rotated 180 degrees. It was just in the SEM that way round. And so this here is our thing that we saw partially resolved. And you can see it's extremely bright. Now, normally extremely bright means one of two things. It might be charging, and what would be the reason for that? And it might be a very, very heavy metal. So the interesting thing about this is that if this was just straight charging in the normal way, you'd normally get very strong bands going across the material, which you don't see here. You don't see here. And the other thing is that you see this dark field all the way around it. Now, again, you do get this when you've got material that is charging, but you know, the combination of things is like, I would have said that this is, looking at that, having looked at a lot of SEMs, I would have said that this was possibly a very heavy metal, and heavier than any other metal that I can see, apart from maybe the little bit down here or something, but even that's not as bright as this. Anyway, before we go and look at that, in fact, we will look at that. We will go into look at this particular structure here, which kind of like has a series of balls around it. It looks like it might have had a trail when it got here. Was it much smaller when it was traveling through here? I don't know. And then it sort of came back into our free space and pushed this material out of the way. Don't know. But let's have a look to see what that is. So I'm going to do that now. So we'll put that over there, and we'll zoom into our piece here, and we will see what that is, and is it of any interest? Well, we've got a spectrum on the top here, which is spectrum 4, and spectrum 4 is, and my computer's dying, is it? What's going on? Right, it's zinc, copper, oxygen. Well, all of those are expected on brass, and quite a lot of sodium, which is interesting. The other thing is that the spectrum 5, which is in the sort of area over here, just on the base area, this is mostly the same. It's zinc, copper, and some sodium. So where is all this sodium coming from? Who can say? Okay. All right. So then we're going to go and have a look at what we thought might be the evil twin of the white one up here, this one down here. Now, this has a soft hexagon structure to it. It's not what I would call super conclusive on that. You can see it here, and in fact I've got a close-up of it here, so you can see it in much higher fidelity when my computer gets up to speed. So it's kind of got a kind of crystal structure, so maybe 1, 2, 3, soft 4, 5, 6, kind of. It is a spherically type blob, and what we find actually is if you have a heavy metal on one side, you get material that is like consumed and it becomes lighter elements, and on the other side you get a whole bunch of heavier elements. And so this is, my view, what the flux loop is doing. And I don't know if you remember, you saw on the bridge that was on the fracture sample from John Hutchison, you had the two monopoles on either side of this valley, and they came and met in the middle. There was carbon running throughout, but from one pole into the dead center, that it was iron rich and other element rich, And it was kind of basically raining out of that and flooding down from that center like coronal rain. And I think you've got a clue there for how coronal rain is actually working. But anyway, that is coming down. And so there's this point which they meet in the middle, and it's a sort of I don't know, you can imagine it, two jets that don't want to mix, and the kind of stuff is spraying away from that. But anyway, we're going to have a look at what this is. It looks quite glassy, and we've seen this kind of thing before here. It's quite glassy, and we've seen this thing before. And it almost looks like it's got a pole itself on the top here, this dark spot. Okay, so let's have a look to see what we have there. And I think I call this evil twin. Evil twin! No! Okay. I'm going to move that down there. That might make that easier. Like I say, this is not ideal, but it is what it is. Okay, so what do we have? Don't break on me. Okay. So, first up we have spectrum 6, and spectrum 6 is kind of like this area here, just over to the left of this little white spot and this black divot here. And what do we see? Well, on weight percent, we've got 52.79% carbon. Atomic percent is nearly 68.4% carbon. Nitrogen 5.12% and 16.91 oxygen. So if you look at the atoms there, you've got what, 68.45 plus 5, 73.5, 83.5, 89, 90% of that roughly is CNO. And this could be the stellar cycle, the carbon, nitrogen, oxygen. So, you know, essentially you've got carbon and oxygen are tri-alpha and quad-alpha, and then you keep pumping protons and it moves around in the loop and it produces, what does it produce? It produces helium atoms. It goes around in a loop, you keep firing protons into it, it goes around in a loop, and then it keeps chucking out helium atoms. So that's interesting. But here we see this sodium at 3.3%, but also, you know, these levels are much lower for the atomic ratio. And really, you typically don't consider things that if they're under like 1% with EDX. However, you've got 3.45% chlorine, you've got 1.09% potassium, you've got some calcium creeping in here, almost no copper, 2.49%, bearing in mind this is majority copper, and actually quite a lot of zinc. And what we found actually in the 10 yen coin exposed to a Mars gas is the copper gets eaten away, but the zinc doesn't seem to be eaten away. And could it be because copper is paramagnetic and zinc is diamagnetic? I don't know. Maybe. Or maybe it's that the zinc is actually being synthesized. Zinc is actually, it's quite hard to, if you're synthesizing elements, to push beyond zinc. And that's just an observation from the Lena field. And maybe that would account for all of the zinc that we were discussing on Saturday being found in an ash from a certain event. And so anyway, there's a lot of zinc there. But of course you have zinc already in the brass. So you can't discount the idea of concentration. You also get some silicon, phosphorus, low levels here. But the majority of it is CNO in this area at the top of this evil twin. Now in the center, spectrum 8, let's go down to that. I'm going to move this down so we can see spectrum. No, let's go to spectrum 7. So spectrum 7 is this lighter area over here. So let's see what spectrum 7 is. Spectrum 7 is, okay, so spectrum 7 has no nitrogen, and it's almost one-to-one carbon. It's like almost like carbon monoxide, 44.91 atomic percent carbon and 44.34 atomic percent oxygen. So you can see that between those two, you've got 83% is that. So we've dropped 7%, and is that the amount of that was nitrogen here? 4.6, no, 1. It's genuinely dropped in all areas. The sodium's 2.7%. Copper is again extremely low. The zinc has dropped down more, but that is this part of the structure here. Now let's have a look at spectrum 8, which is this central spot, which is light here. And I probably expect, I can't even remember whether I bothered looking at this, okay, this is interesting. So in the spot 8 here, we have a very nice broad spectrum here of elements. You see all of these very clearly resolved lines. We've got carbon, nitrogen, oxygen, sodium, aluminium low level, silicon low level, phosphorus getting up there, sulfur that we've synthesized before, chlorine, potassium, those are registering at levels that are meaningful. Calcium still quite low. Iron we've got creeping in there. Iron, interestingly, at this point. And often you see these two spots like with these things. The copper again is about the same level, and the zinc is midway between the two. And I think what have we got? We got one which is maybe out on the debris field out here. So out here on to see what the base material is that it's sitting on. So let's go and see what the base material is sitting on, which is 9. And the base material is, okay, the base material is almost no carbon whatsoever, a little oxygen, which might be the oxide of that, and there we can see it's basically mostly copper and zinc, but there's twice the amount of weight in fact it's pretty much exactly twice the amount of zinc to copper, which is not the ratio that should be there. So copper seems to be being consumed even on that kind of area. Very high concentration here, atomic percent of sodium. So where is all this sodium coming from? I wonder. Anyway, so that's that. Let me get the main event here in this part of the presentation. Okay, so this is what I wanted to know out most when I was preparing my as easy presentation. What was this? What was it? And I guess before I show you, I'm going to pull up a image from our friend Ken Shoulders. Why not? Why would we not do that? How does my machine run so impossibly slow? Okay. You know what? I'm going to get rid of that because it takes too much memory. Talk amongst yourselves. Give me a sec. Right. So this is on Rex Research, and this is the diagram of what Ken Shoulders said an exotic vacuum object looked like. Now, I should probably know this by now, but honestly, I don't. I don't know whether this is what he saw in flight, or whether this is what he saw under the scanning electron microscope that he had at the time when he was able to image a device, image this and draw a schematic of what it looked like. But these genuinely do look like spheres. They really do look like spheres, and they are arranged. You know, they are attracting each other, obviously, but they are also repelling each other because they're not linking physically together. And I think that's actually very, very important. But I had this in my mind when I saw this particular structure. And we're going to zoom into our little structure here. Why not? So the question is what we're seeing here something similar to what Ken Shoulders drew over there? Well, it doesn't have this, how should we put this? It doesn't have this, my machine should never be this slow. It's just unreasonable to have it this slow. It doesn't have the crystal structure that you're getting in the background here with all of this copper and zinc and whatever else is in the background. And unfortunately, because it makes it so dark, you can't see so much going on. But it definitely has this sort of penumbra, this kind of like glow around the outside. And it's very subtle, but it would appear that Ken Shoulders is showing something similar here. He's also showing something that's darker in the center, but he's got a bit of a reflection here. And I don't know, but this wasn't convincing me that this was the same thing. So, of course, what you would do is you would zoom in. And so this is what we see when we zoom in. And then I'm looking at this thing and I'm thinking, well, is this just a different scale of one of these things? We're definitely seeing something darker in the middle, and you could argue that this is darker. And I don't know whether this is a torrid. This isn't D4D ratio. So is this some sort of field fall-off that he's got here, and this varies? And if that's the case, is that what we're seeing here, this kind of like glow? And like I say, you know, the material behind is completely black at this point. But if I play with the contrast in Photoshop, we can sort of pull some of that out. But it's definitely got this darker area inside, but I'm still not convinced about this, okay? We worked hard to try and resolve this better, because it would seem that it was sucking electrons out of the environment, out of even the electron beam that we're firing at it, and it's making this thing glow unreasonably or make it fuzzy. But that might just be a focus issue. But it's a bit weird because we seem to have this hard and reasonably well focused edge here. But then we have this kind of, and also this fairly well resolved edge here. But the rest of it seems fuzzy. It's almost like it's got its atmosphere. It's like a planet with an atmosphere. And is the atmosphere the electron cloud that it's captured? Anyway, with a lot of hard work and changing with beam energies and whatever, contrast actually, not beam energies, but we ended up with this. Well, isn't that nice? Isn't that a thing? It's wonderfully smooth, okay? But it has these kind of like Almost like a pine cone. It literally looks like a pine cone. Yeah? But it looks like a very smooth version of a crenellated sphere. Or it might be, you know, something similar. Now, the thing that threw the imaging off at the lower level, when I show you this one, this kind of made a weird highlight. It would appear is a piece of material that's either born on the surface or captured onto the surface. But the other interesting thing is that it seems to be spherical in nature, but it actually has this dark point in the center. Almost like this is a pole, and the electrons are being sucked into this pole. So if I was to look at this, I would say that if this is the core, the magnetic core of a monopole, I would say that this is a south pole. The electrons, or whatever it is that affects the electrons, is being sucked into this pole. But it is still, in my view, a sphere. And so is what Ken Shoulders was looking at here, did he see something like this? It looks a bit like a kind of donut that doesn't quite make being a donut, but I think it's actually a sphere, because when you look at all the other geometry. Now I'm going to pull this into Photoshop, and I'm not done this before, so we're going to play around with the contrast. I'm not finishing with this, by the way. What I have to show with you is pretty damn awesome. But we're going to have a little look at this with Photoshop now, so that we can get a better resolution on it. But before we do that, let's find out what it is. Why don't we do that? Let's find out what it is. Never fear a sphere, but very, very wise words. You can't hate spheres, we live on one. Kind of sphere. Okay. Right. Here we go. So what do you think it is? Let's look at Spectrum 1. Spectrum 1 is looking at the top here. It is, drum roll please, 56.29% by weight iron. Over 50% of its mass is iron. And in fact, by atomic percent, it has just 0.93% copper, which you would ordinarily consider is below a level which you would consider it's actually there, but it's on the threshold. And 1.6% zinc. But it is basically copper. Sorry, iron oxide. It's basically iron oxide with a diddly squiddly bit by weight of carbon. This is an iron-rich, probably some sort of magnetic phases. I believe that this is, in fact, the magnetic core of an exotic vacuum object, or the toroidal structures that form kind of ball lightning and this kind of various types of things that Alexander Shishkin is talking about. This is the magnetic core, and I believe that what I consider the weird behavior with electrons is that this is it has a very tight fall off, but it's able to pull in the electrons from the environment. Let's have a look at the other areas which we looked at just to see if there's much difference. So looking at this bright spot here, Spectrum 2, the bright spot here is 16.89% zinc and 2.51% copper. So I believe that the bright spot here is probably a bit of detritus or something that's grown off the surface. And it's interesting because some of these things do come out of crevices. So it may actually be growing off the surface. Let's have a look at the nearly the top. I couldn't go quite to the top because if you look at it right in the top, there's also some more of this detritus off to one side. Okay, the very center would include that if I did a circle. But spectrum 3, let's have a look at spectrum 3. And actually spectrum 3, I might be capturing some sort of imaging, some photons from there. But anyway, again, it's 64% by weight of iron. And so what was the other one by weight? It was 56.29. So the dead center of this is 64.23% iron in the dead core of this structure. Well, iron's ferromagnetic. It's ferromagnetic because it's ferro, isn't it? And so the dead core is more ferromagnetic in material than this outer skin here. But essentially, it's mostly iron and oxygen. It is an iron-oxygen magnetic core. Let's have a look with Photoshop and see what we can pull out. But isn't that a thing? Isn't that a thing? Okay. So I will do what I said I was going to do, which is drop this into Photoshop. If my complete machine doesn't fall over, we'll be good to go. Yes, infidel apostate is self-organizing donuts that create magnetic cores. Now, the magnetic core itself, it might be coherent. And so during the traveling or interaction of the exotic vacuum object, this microball lightning with other matter, the actual core almost would have no dimension whatsoever. It's only when it comes back into our free space that it becomes this sphere. And remember what I said, I believe oxygen is critical to the way this works in water and a Marsa gas and a Brown's gas and whatever. Because oxygen is very paramagnetic. It has this high magnetic susceptibility, which none of the elements anywhere close has. And I think oxygen is absolutely key to transmutation where you have any form of water involved in whatever system it is. Oh, when will this end? Sorry, I'm just talking about the slowness. It doesn't help that it's an 8,000 by 8,000 pixel image. Well, actually, this one may not be. I can't remember. No, this one's 4096 by 4096 pixels. So here you actually can see here, and it almost looks like it's within the atmospheric realm, as I say. And the top and bottom, there is a little bit of band, which may be the interaction within the atmosphere of where it's interacting with the electrons. I don't know. It's just you can definitely see that there, but you can see a little bit more of the background here. So I'm going to play around with the contrast here so that we can maybe pull out some details. So here, if I pull this down, that will get rid of the background. If I pull it down to here, you can see. Really, I mean, is this verging on being a torus with an infinitesimally small hole through the center? I mean, is the sphere actually that, or is it actually a sphere but it's pulling the electrons in? And so you're getting the no, I think it genuinely is a sphere. Or if it has got a dimple in the top, it's kind of like, how should we put it? It's a bit like an apple. The Earth is like an apple, whirling silently in space. Something like that. Round like a circle in a spiral, like a wheel within a wheel, never ending or beginning on an ever spinning reel. I can't remember and play with this. So you can see if I play with the contrast here, you'd get a very different idea of what the structure of this thing is. And this again is the advantage. When you are doing SEMs, you should always capture 16-bit. But from what I see with these sort of plates or whatever, it doesn't appear to me, well, it may do, but it doesn't really appear that this is dipping into the center, but maybe it is. Maybe it is. I think we need more investigation. Now, this does look like it's going in a straight line. I think what we are looking at here is the pole. This is the magnetic pole, and I believe that this is the south magnetic pole. And that is why it's sucking the light out of the room. In this case, the electrons. Yeah. I believe that what we are looking at here is the magnetic core of magnetotoroelectrical radiation, string vortex solitons, ball lightning. Yeah, you see, if I change the contrast to here, you know, it's basically a sphere, right? There's a little bit of a fall off here, but I don't see, look, so we can actually see here now, if I go in, because I've got the pixel, so let's do it. If it can allow me to zoom. Oh dear, sorry, my computer's going to catch up and it's going to zoom in and out about 10 times. Oh dear, I do push the limits. Okay, come on. It's literally stopped. Great. I'm waiting for my computer to give me back control. So just bear with me. I don't see particularly a dimple in this center. I just see something. It might be very subtle. It might be very subtle. But I see something that is absorbing the electrons. Okay. And this is getting beyond a joke. Can't cancel that. I'll zoom in. So we'll zoom into this center bit. Okay. So we're right in the center here. Okay, and then we'll pull up the levels here. Now, what were we doing? We were doing that, weren't we? Yeah, you can see here. This doesn't. Maybe it does dip right in that very center there. I'm learning this at the same time as you guys, so I'm going to really push this to the limit here. So is that dipping right into the center here? We've got like a Star of David here. This looks like the point at which everything gets sucked in at the extremity. And I'm running out of resolution here. I don't know. I just don't see it. What I think is that this is, if anything, it's just got a little dimple there in the top, and I think we have a spherical structure. But this is the magnetic south pole in my view. I'm 50% likely to be right, and whatever is going in there is taking the electrons with it. Yeah, okay, so there we go. Right, I think we can move on now. And we can have a look at something else. Does anyone have any questions at this point? Is the sphere hollow? I suspect it might be when it gets bigger. In the ones that we had with, if I can find it, with, if I go, I'll get it for you. If you go to remote view and look for, I think, the coherence presentation. Where is it? Yeah, if you look at ball lightning coherent nuclear transmutations, this one here, Alan found a fragment which he took an SEM of here, and if you look at it, it is on the inside. This is atomic concentration, so it's mostly where are we? 2138, 2138 up here. Unfortunately, he didn't look at this side, but this looks like a skin, and the skin, if this is 40 microns, then this would be 20, this would be 10, this would be about 2. It's about 2 microns thick, and then it has these platelets on the outside, and I'm wondering if the platelets aren't what we are seeing here. Yeah, these plates on the outside, almost like dragon skin. Yeah, like a fur cone, like a fur cone. So I'm wondering if this isn't this, and then this is the inside layer. This would be the inside of the double layer, right? And so this is completely amorphous, and then this is this kind of hexagonal, again, like cell structure, which might be the itonic cluster on the inside. So I asked him to run the experiments again if he could. He hasn't had a chance to as yet to find out, because this sort of looks curved, but it might be that this whole thing is a ball that unraveled itself. So like, you know, we're looking at one pole here, and these 3 bits come together into some sort of sphere, and so it might have unraveled itself that way. So I don't know, but this was one potential interpretation I had, and I'm glad that he took this. I said here, could this be part of an unwrapped sphere that was partially hollow? It appears to have 3 types of structure in it. Its thickness, one that is amorphous in the center, and one on the underside that may look like the outsides of other spheres examined, but cannot be sure, and an inside that is a cellular structure that looks a little like the surface of the sun. And I agree, this really does look like those images that you get of what the surface of the sun looks like. Okay, so that's the best answer I can give you to you, is this hollow inside, because we have considered that before, and I think with more ultra experiments and times on SEMs, I said, like, you know, it would be great to run an ultra experiment. You bring the distilled water, you bring the cleaning thing to clean out the tank, you bring the aluminium foil, we'll look at the aluminium foil afterwards, we'll spend 2 minutes doing the experiment, and then we'll put it under the SEM once the sample is dried, and we'll see what we see. And we're going to look at that later in the week from the one that I did, and I think that's going to blow your mind. But anyway, we've got some really exciting things to show you tonight. But anyway, yeah, so that's what I can do there. So does anyone need any more contrast just on this particular structure? Because as interesting this is really a kind of like letting you know. I said as soon as I can get in the SEM, I will take a picture of this. It's from first on my priority. I did. This is what it was. I think we've learned a lot from it. And but it isn't all I found. And I spent a good sort of 8 hours or 6, 7, 8 hours on the sample, And like I say, I could probably spend several months on this particular sample learning its secrets, but I think the next couple of secrets are going to be very nice. So now one other area that we found on this particular sample, which I'm going to show you now, which was in this same area as the evil twin and so forth. Let me find it. Is this one. So I'm probably going to shut down that because it's going to slow down my machine. If I don't. Oh dear. I'm running nothing. Why are you so slow? Okay. So I have this little beautiful thing here, which is in the same sort of area. And it looks like a splat. So this is the kind of background area here. And it has this sort of polar area here, where it has a secondary splat on it, which is kind of over the top. And I've got this in beautiful res, so we can go and have a look at the substructure in here. And these these substructures in here look a lot like a micro version of what you're seeing over here. Oh dear, you would be seeing if my... Oh, this is just tedious. Got to get this sorted. Right, you can see these platelets here, and so these are kind of like a big version of these little things down here. So what are we looking at here? That would be interesting to know. But I have to say that when I was looking at this, and I haven't compared it, so I'm going to have a quick look now, to some of the things that Matsumoto observed in his experiments. Of course, he's dealing with different materials. Yes. Oh, there we go. I rest my case. So, firstly, oh dear, memory's a wonderful thing. Oh, Matsumoto, you've got to give it to him. Oh dear. You're not going to believe what I'm about to show you. Right, hold this image in your mind. And I've only just seen this, but let's have a look at what we see here. Right, ready? I'm going to hold it up at the same time. Look at what Matsumoto observed here. Right, look at what we've got there. I'll go out here and we'll go in full frame. So there we go. Can you see it? Can you see what it is yet? And I observed something similar to this and to this here on the underside of a piece of titanium exposed to a Marsa gas that was done by Sho. Thank you very much, Sho. And he sent it to me, and I observed this thing, if you recall. A similar kind of structure with this kind of like, it almost looks like a coconut with the top of the coconut, and then there's this little bit at the top here, and you just couldn't believe it. You couldn't make it up. Nature does the same thing every time, but this is the different elements, by the way. It's different elements, right? So you got the splat, you got the top of the splat, and then you got the top of the splat. Right? It's just the same thing. Oh, Matsumoto. What is that? I'm going to have a look at what that is. That is image 8708C. 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 87. Oh, that might be at the other end. Really? No. Okay, I can't find it immediately. I'll have to come back to you on that. The other thing I've just noticed is look at this ball here. Look at this ball. That one. Can you see it? This one down here. Got to give the guy credit. So I think this is a microball lightning payload, and it's been dumped here. So why not? Let's us find out what this is, and it is. I've done several sample areas here, and we will zoom in so that you have a chance of being able to read it. Oh dear, where did that go? Splat, there we go. Okay. So, spectrum 13 is here. And, sorry, spectrum 10, let's start with 10. 10 is this big structure here. And 10 is 9% sodium by weight, 10.5% by atomic percent. It's 4.29, so it's almost like it's salt. Now, is salt something that was born at the birth of the universe and just happened to be part of our planet? Or was salt synthesized? Because I think if you go back, you'll find a lot of sodium is synthesized in Lena experiments. In fact, maybe I can go back to that particular presentation. Where is it? This one. Okay, and we are looking for what really is the new fire fuel from 3 years ago, 3.5 years ago. No, that's about black holes. Okay, what really is new fire fuel? So let's see if we observe sodium. Actually, those guys didn't see sodium. Well, there we go. There we go. They didn't see sodium. Can't always win. Okay, so spectrum 11, this one over here is it's got some copper and zinc in it, quite a bit. Yeah, not so interested in that. 13 over here, which is this funny structure here. 13 is down here. Yeah, mostly copper and zinc. Chlorine. Yep. So is this some sort of actually hold on, this is this, it's 43% zinc, so maybe it's some sort of zinc compound, I don't know, but it's very ordered. And where was that? Is 13. Anyway, I'm going to move on because 12. This is this kind of layer up here that's on the top, exactly as Matsumoto had observed. What was the layer on the top? Spectrum 12. 12. That is not very interesting. It's just a feature, really. Does it have significantly difference? 24, not really. What's different about it? Oh, it has some sulfur in it. I don't know whether that's that different. Anyway, there we go. Obviously, I'll share the data at times, but I think the most interesting thing here is that when I took it, I thought, I swear I've seen something similar. Well, I saw something similar on the titanium exposed to a Marsa gas, but literally that right there by Matsumoto here is almost an exact perfect thing, but with different materials. So there we go. It is the same phenomenon. Okay. So then we are going to look at another area on the Vega Valley. In fact, we're going to look at some wonderful SEMs of the Vega Valley. And I'm going to kill Photoshop for now because it's just hogging resources. Okay. So we're going to have a look at this particular area, just because I wanted to see some close in on some of these structures here. And actually we've got this at a lovely pixel density here, so we can see this with some high fidelity, even without changing images. And so I'm interested in these couple of splats here, which I go and have a much closer look at, which you can see here. And you can see how the plasmoids are interacting with the surface. And you can see how some of them have burrowed into the surface here, like there. And over here, a couple of boreholes into the surface. We saw some things similar to that on Saturday. And I like the way that it's kind of like produced these structures around here. And it has this very, very discreet fall off, like that we've seen when it's cutting materials. Absolutely, extremely precise fall off with its interaction. Really quite beautiful. And in fact, I've got this one at even higher resolution, if that wasn't enough. And then we will have a look at this. So here we go. So I think this is rather nice. Is this a pretzel? Like the pretzel is in here, and this is the outside of its interaction field. I don't know, but what we can say is that this is kind of like swept over here, and then maybe swept over here, and then swept over here, and then swept over here, and then swept over here, and it's kind of going round in like a loop-de-loop, a loop-de-loop, loop-de-loop. So it's almost like twisted in on itself. It's probably clearest here, maybe not. So I think this is coming round here, and then it loops down on itself, and then it comes through here, and then it loops around on itself, and then it comes around here, and then it loops round on itself, and then it comes around here. So it's pretty stunning, I would say. I think this is one of my favourite pictures of the day, but not the most favourite picture. You will see that, and it is pretty amazing, really, what I have to share with you. It comes around here and it loops around here. So is this a number of EVOs that did this damage, or is it one, or I don't know, but I think that's rather fine, don't you? I think that is rather fine. And look how precise it is with how it interacts with the material. It's like this is the substrate, which of course has been affected by other things. There's a little one here that's chewing into the surface, but this is very, very precise. You can do that with a laser pointer. Oh, you're not talking to me. You're talking to a different Bob. My question above for you, infidel. Okay, all right, fine. Okay. Yes, David, you simply cannot see this level of detail. So what we are looking at here is 100 microns. So it's actually still quite a large structure. This is, I think you can get pencil leads that are this big. So it's 100 microns there. So I guess the width of this there, for instance, is at least 5 microns, I would say. 5 microns. So is this one Evo that's just moving around in the surface, or is it a collection of them that did it? I don't know. But I think that the way that this is folding and looping around itself, you can imagine that if this section broke off and flew out, it would create one of those coherent matter traveling waves, you know, with some weird structure, which kind of makes sense when you see it solidified here. I think we're going to learn exactly how those things are made, given a little bit more effort. Time and effort. Yeah. So let's have a look at what this is. So give me a second and I will find the data for that. If I did take that, I think I did. Yes, I did here. Okay. I took plenty of sections on this. Okay, so I took all kinds of things here. How exciting. Right. So here you can see, I might have even taken some, I intended to take some map of this. I don't know whether I did. We'll find out. So spectrum, what's the first one here? Spectrum 16, 15, 14. 14 is this, the outside here. So 14, I'm going to look at the outside here. So what is that? It is carbon and oxygen, and it is mostly copper and zinc. Well, it's brass, and there's the sodium there. Where is that sodium coming from? Where is the sodium coming from? Where? Okay, I won't push that too hard. Right, so that's the outside is brass with some bonus sodium. 15 is this particular ridge here. So 15 is this ridge here. And what is that? What is 15? 15 is, ooh, look at this. We've got a bit of iron creeping in, not much. Copper and zinc, this is mostly zinc actually. Again, we're seeing a situation where the copper, is that right? Am I getting it right? The copper was, oh no, it's the same, 1654.76, 1658. Yeah, there's more zinc here. We've got sodium, but we've got aluminium, silicon and iron here. What do we have up here? We had aluminium, silicon and iron, so not much different. It may just be moving the material around. Okay, so that's that bit there. It's a shame we didn't look at this bit over here because this looks very different. Okay, so what have we got next? 16, excuse me, 16 is the inside. What do we see there? No. 16 is there. Okay, so 16 is the inside, and it is mostly copper. No, mostly zinc. More zinc in this place. Yeah, not so much interesting there. So it does tend to be looking like the bulk of it is just shifting the material around and churning it up. So I actually called this sample mix, as in it's like a cement mixer. It's just mixing the material up. Oh, this is tedious. So hot in here. It's very hot today. Okay. It's Microsoft. It's just Microsoft. The computer is not even running hot. It's just Microsoft. How do they make such bad software? And they've been doing it so long. Right. Okay. So 20. Where's 20? 20 is actually 20 is this little kind of like seed-shaped piece here. Spectrum 20. Okay. What is 20? 20 is phosphorus, sulfur, calcium, zinc, copper, of course, sodium, and 58% by atomic weight in atoms are carbon. So this is interesting. Again, it looks polar. It's got a dark end at this end. So that's that one. And spectrum 18 is the top of... I'm not going to zoom in and out of this because it's just being so tedious. So, okay, so spectrum 18 is this top over here. Okay. I despair. All right. And so this top here, this kind of splat on the top here, spectrum 18. Oh God. Maybe I should have found a few hours today to do this beforehand. Sorry. Spectrum 18 is 67% carbon. So that's carbon on the top of that. And usual suspects elsewhere. There's a white blob kind of like over on the right here. I think we look at that. So there's two kind of like amorphous kind of materials. It's going to let me do it. Yeah, so we got one little amorphous blob here and another kind of a amorphous stuff here. So I think we're going to look at these two and which one's what. The first one is 17 and the second one is 19. So 17 is 73.93% carbon, this one. Almost no copper. Zinc's nearly gone as well. So it's mostly carbon, nitrogen, and oxygen. And it's this film structure, just like Matsumoto observed. And again, we've got this folded film of a particular thickness. We can have a look at the thickness in a second. And that is 19, was it? 19? And that is 63%. In fact, 63 plus 12 is 75, 76, 86, 90, 90%. Again, that's 90% carbon. And it's, how thick is that? So this, I believe, is the kind of carbon film that Matsumoto was observing. And that's 100 microns. I don't know, it's about 10 microns, I guess. No, 10, it's 5. It's about 2.5, 3, 4 microns. Okay, so that's that feature. Now we're going to do something very different. And I don't know which one I want to do first. I think I'm going to do this one first. Okay, let's get this out of the way. You're going to like this. No, I'm not going to do that one first. I'm going to do this one first. These are really, really big files. So you might recognize this. This is a section of the Vega Valley. And we've got this in beautiful res. So we can go right in and really understand the structure and the cellular sections on the cell walls here, or the channel walls, and the steepness. You can see how steep it becomes. It's really, really easy to see that in these images. Okay. And you've got this sort of flow through area here, which is quite interesting here. One area into another. Oh, it is so slow. Oh dear. Right, and then I'm going to look at a similar section to the right of that here. And you'll have seen this caldera before. Okay, so we got our kind of caldera. It's not really caldera. But again, you can see these splat areas. And I'm going to talk more about how the magnetic fluid creates these structures in the future. But it's really quite spectacular. And it's lovely to be able to have this kind of level of detail and be able to look around it and understand what in my view, is a magnetic fluid did to create this channel and the kind of forces involved. Okay, so in the next image, I believe it is, there is something that I spotted. And I thought, ooh, what's that? So, this is the image which I first spotted this structure in. And it led me down a rabbit hole, which I could have probably spent all day looking around the sample for similar structures in similar positions. And given more time, that's certainly what I do. I've got a mosquito joined me for the evening. That's nice. Okay. So, yeah, so you've got your coherent matter stuff that's moving around here. This, what I call fluidized electrons. And you can imagine that these are ball lightning that have wetted into each other. And they both repel and attract each other, and they form this magnetic fluid that runs around in these channels and churns up the material. Okay, now I'm going to zoom into this area, and you'll see why, but it's kind of like I kind of spotted it from the far view. And the reason is that I spotted something here, which is, in my view, precisely equidistant from the tangent perpendicular on this curve, the tangent perpendicular on this curve, and the tangent perpendicular on this curve. So it was dead center. And I thought, this looks like something that's very, very significant in terms of the field. Okay? So I zoomed in, and I zoomed in, and I thought, well, I'm not going to see much here, am I? This is kind of like the same sort of story that I had. Oh, dear. Come on. Is my machine stopped? Yes, it's stopped. It's not even hot, it's just stopped. Maybe it's low on memory. I don't know. It's stopped. My machine has just stopped. Okay. Right. And bear with me, I'm going to reset my machine. Oh no, I've got my mouse pointer back. Is it going to let me do something? I think it's given up reporting the temperature. Okay. Well, what I'm going to do is I'm just going to go straight to the next image. But the structure we're looking at... no? Oh, okay, that's not good. That's not good at all. I've never seen that before. Oh, dear. I think my machine's died. Okay, that was a reboot. Without me asking it to. Okay. Now, fortunately, I have a separate machine. Oh, that was interesting. Okay, it's popped back. It kind of like did I don't know what it did. I'm pushing the limits here. Okay. I've never seen that with this machine. That's the first time you got to see it the same as me. I'm worried now. This is not the Blue Screen. This is a Mac. This is a... I don't know what it is. Oh dear. Now. I've got a weird... Okay, alright. Okay. We've got something back. Maybe this is all I need. There seems to be bits missing, but... Right. Let's get back to the science, shall we? This is going to be worth the wait. It's going to be worth the wait. Sorry you're having to wait, but I've got to find a way. when you're playing around with very large images, it's you're always asking for trouble. But anyway. In the moment it's rebooting all the programs. I didn't ask it to reset, it just did it. I mean, it is running very hot. Why did they make these machines so bad? It's a really fast processor. You can use it 1% of the time. Okay, it's literally restarting everything. Okay, sorry. This is tedious, I know, for you guys. What can I do? You are. It is worth waiting for. This really is worth waiting for. Oh, no. Good. Yes, Drav. This is really, really worth the wait. I'm not joking. It really is worth the wait. Okay. No, I didn't want to do that. I feel like someone trying to fly a plane where the air density is so thick, and I'll like try and move this way, and by the time the computer's covered off, I'm all the way over somewhere else. On the plus side, I've just got the mosquito. I don't have to worry about that anymore until the next one comes in. All you are doing is showing images. I think I might do this on my phone next. Okay, we're nearly there. It did a full machine hard reboot of its own choice. The first time I've seen this Mac since I bought it completely crash and burn. Okay, so what are we looking at? We are looking at this one. Come on, you can do it. You can do it. Preview one image, that's all I'm asking. Okay, so where were we? We were here, and I was saying that this particular structure here is equidistant from the perpendicular of the apex of these three structures. And I thought that was interesting because that would imply to me something field-like. And so I decided to go in and look a little bit closer, and this is what I saw. Not that time thing. I saw something more interesting. Here we go. I saw all these lovely little nodules and something right in the middle. And so we'll look into this a little bit. Isn't that lovely? Wow. Isn't that lovely? So it's in a kind of pit. It has a sort of semi-hexagonal form to it, and it has this ejector on it. But you know me, I'm not happy with looking at something that close. I have to go in closer. Look at this puppy. Look at this beauty. So, I'll tell you what this reminds me of. It reminds me of a pomegranate. Yeah? The fruit or that the Sumerians used to like to hold up in the air. The Sumerian gods, they used to hold up a pomegranate. And in fact, some time ago, I included a pomegranate on one of my videos for this very reason. Actually, that's why I included it. Let me see if I can find that frame. Just going to zoom into this a little bit more so you can enjoy it whilst because I'm not just finished. I'm not going to stop there, am I? When I'm going to zoom in, I'm going to zoom in. I mean, I'm going to zoom in. Really, zoom in. This is just not a molten blob. This is not a molten blob. I mean, this is like an electronic, like this is like lightning. It's like made of lightning. And what you see on the inside here are these perfect hemispheres. Really incredible. Like little water droplets on the inside of this structure. And it's almost like it's twisting. It's twisting a little bit, like there's a vortex running around here. A vortex. You can see the angle here. The angle down there, angle there, angle there, angle there. And over here, angle, angle, angle. Yeah, it's like a lot of natural things. And the inside structure is, you know, floury. It's like a sponge. But all of this is contained within this thin skin. And before I go too much further, on the outside of this, what do you see? You see our triangles. Our triangles in various scales. There's another one, little one down there. Some of them are pointing in. So is this structure made of monopoles? Like, okay, so 10 micron here. We're going to talk about the scale. Again, I'll show you the kind of structure down here. Look at this. It's just stunning. Very, very ordered. This is not just a piece of molten material. It looks like a piece of life. Now, whilst you are looking at this, I will Okay. I'm now going to get what I was going to show you. Oh, it does that when I do that, which is tedious. Okay. I'll leave that like that. So give me a second. It gets interesting when we find out what the elements are. Now, I'm speculating that maybe the itonic mesh is something that binds these segments together. That's my speculation of the evening, and your mileage might vary. And that this is a pole, and I believe that what you're looking at here is a north pole. A north pole. Now, on a pomegranate, that would be the south pole, like, you know, where the flower is. But no, I think it's the north pole. I'm just going to look to see if Matsumoto observed something similar, which he probably did because he made some effort a few years back. I can't help thinking that this kind of structure is similar to this one here, where you have a round structure and then something is coming out of the top. It's coming out of the top. And remember what Solin said, that it produces these spherical structures, and from inside the spherical structure, the nuclear reactions occur. So this one here, where is it? There we go. So we got a structure here, and something's coming out of one of the poles. Yeah, coming out of one of the poles. This one here, where it's like almost like a flower, right? It's broken open. But I think that this is more significant because of the placement in the overall sample. So let me find what I'm referring to, and then I have a challenge for you. But we are not done. We are not done by any means, because I've got the big reveal to close out this presentation this evening, this microscope review session. So I will and I want to find this. I want to go here. I want to go So if you go to YouTube and you go to the MFMP's YouTube channel and you search for Learning Lena from Sun 2 Proton Flare, you will see this. You'll be able to download the presentation slides. And you will see this is the first slide from the presentation. And my game for you is to find out what I put in the background many moons ago. When it's finally downloaded the image. Oh dear. Here we go. So there we go. That's our pomegranate. Slight rotation. What I want you to do, this is my game for you, is to try and find out what I have in the background here. What I have in the background. Where does this come from? I'm not going to tell you. I'll tell you when someone's worked it out. But I believe that this ancient symbology is an indication of the monopole structures, and I think they've quite accurately represented the triangles that it produces and the overall structures and the field structures. And you have to wonder how this particular culture knew this so accurately. But anyway, I chose this pomegranate because the Sumerian gods saw this as a symbol of their understanding. And there we go. Right, we are going to find out what is in here. Let's do that. Let's do that. But what I'm saying is that this structure is an electromagnetic structure, and this structure is an electromagnetic structure. And nature, the seed, all of the seeds, in my view, for the forms that are made in nature are being created possibly by exotic vacuum objects and the way that they cluster. And the amusing thing here is that Ken Shoulder said he called them exotic vacuum objects, but he said they're ubiquitous, i.e. they are everywhere. They are absolutely everywhere. Okay, so we are going to pull up the SEM data here for this. And what I did actually with this is I took an image map. Oh dear. Right. Interesting. It looked like it was actually Excel that crashed the system. Which does not surprise me. Oh no, is it going to crash it again? I've just opened an Excel file. Really? Seriously? Okay. So, the first thing we can say about our structure here is the scale of it. Now, as we know from Bostic, and we've observed this since, they have a particular structure to them. And if we look at the inside of this part to the outside of the shape, we have 13.4 micrometers. And we have across the width onto the inside edge, we have 53.4 micrometers. Now, around about 50 microns is one of the classic quanta of exotic vacuum objects. And we observed this type of scale, if you recall, on the structures that were polarized on one part of the Vega Valley, and also as the type of scale of a pair coming out from the side of the Vega Valley walls. But the interesting thing is here, if you times 13.4 by 4, you get 53.6. So this is approximately a D4D ratio structure. where this is the hole. So is this actually a kind of torus? And the material here is being pulled through the torus, and it's building this structure out from what's coming through. And did this happen nearly instantaneously when this thing struck the center? Why I don't believe that particularly is because it looks like whatever this is, it did a lot of work to organize the entire environment around it. So all of these things, like there is a radius around this, and they get bigger and they get bigger and they get bigger. And then this is in the center of these 3 channels. And I believe that its influence was absolutely key to the formation of this 3-way channel, which we see here. It's this structure here in the center of this channel. I believe that this thing, equidistant from these 3 channel walls, is the structure that organized all of this matter around it. Okay, so what do we see? Let's have a look. In the spectrum 30, which is on the kind of outside area over here, I can go in one more. So spectrum 30 is just outside of our, let's call it the pomegranate. Oh no, here we go. Why? No. I don't want to check for updates. It's already bad enough. Oh, God. What is wrong with Excel? I will publish these images. Okay. Come on. Give it to me. Okay, so on the outside is spectrum 30. And what does spectrum 30 have? It is bit of carbon, 9% atomic carbon, 18% oxygen. It's got 9% sodium. Interesting. And it has mostly copper and zinc. Well, it would do because it is the starting material. What does this area here on, let's call it the donut part of the overall structure. So that's that is 27, I think. So 27 is less sodium, 3.69. More copper than zinc on this outside here. This is interesting. So the wall, so outside of the pomegranate, 30 was how much copper and zinc? Was still more copper than zinc, okay, but 36 basically to 27, and 27 is 61 to 30. So it's a lot more copper. This structure has a lot of copper on this outside bit. What else can we find out? I'm looking at this black structure over here, which almost, if I look at it close up, it almost looks like a hole. It looks like you're looking inside something hollow. Look, it looks like part of the skin has fallen away and it's produced this hole. So I decided to look at what this was with a circular section. I choose this to be section 30. So this hole that I'm looking at here, what is that? So I'm kind of peeking into the inside. What do I see? 32. 32. What is that down here? 32. Okay, well, not much change on the copper and zinc. It's got a little bit of iron in there, a bit of sulfur, but not too spectacular. Again, you can see we have one of our triangles here, and we have another triangle here, and we have another triangle here. Okay. So if you can imagine one of these things blowing up, if these were loads of monopoles that are in the larger structure, then they would all fly out and leave their mushroom traces on things. Okay. I think we're going to get a very good idea of what these things are before long. Just a bit more work. Okay. And let's have a look at what spectrum 28 is. So that's this kind of like stuff in the middle here. This kind of bit, I've looked at this area here. What is spectrum 28? So let's have a look at that. Okay, so spectrum 28 has 8.17% sodium. And it has a lot more oxygen than, I think, than other areas. Oxygen, 2.2% there. Yeah. 28 and 29. 29. Where's 29? 29. Ah, 29 is the top of one of these structures over to the side. Let's have a look at that. So now the thing is, I've actually got a map of this, so it'll probably be a lot clearer what's going on when I show you the map. You'd be like, I could have saved a lot of time, just show them the map. So 29 is the top of that one. I'll go down here. 29, top. Okay. So we've got some potassium in there. Okay, and a little bit of sodium too. Right, so let's have a look at a map of this structure, because I think that'll make it very clear. Look what's happening. Look what terrible piece of software. It's just so appalling. Can't believe we're in the years we are. Here we go. Here we go. So, copper and zinc is pretty much everywhere. Okay? But the interesting thing is, in the center here, it's rich in sodium. It's rich in sodium. And over here, it's rich in oxygen. Now, I haven't done the tables yet, and I'm not going to do them now because I want to get to do the last thing that I want to show you today. But could this be a plume and it's spraying out sodium and oxygen from this interaction with the brass, with this structure that's got a lot of copper in it? And it is synthesizing sodium and oxygen. And if it is, I would believe that this is a south pole, and it's a north pole rather. It's a north pole, and so it's making a lighter element from what it's consuming. It's making sodium and oxygen, and it's spewing it out of this plume. Okay. And so that is my assumption. So I think we have seen a North Pole and a South Pole today. So the South Pole being the first and the North Pole being the last. This is highly speculative. You are literally seeing near real-time looking at this. We also saw this toroidal EVO with a depositing its carbon. And so what I thought was, given that we saw this in the center of, a free branching channel, I thought, can we see any and I was running out of time, and I thought, can we see any structures in the center of a channel that might be another magnetic core of a EVO? And so, so it was basically this here that we saw. When it comes up, this one here, and this ended up being our structure that we've just been reviewing. This one. Okay. So let me find the right channel, and the right channel is here. So you will have seen this in full glorious color in some of my. In fact, it was the first image that I shared that I took with the Sony Alpha. And what I was looking for is something that's kind of in the center, And I spotted one here, I spotted one here, I spotted one here, I spotted one, you know, up here. So I just thought, well, let's just pick one of them. There's another one over here. So I just thought, let's pick one of them. And this one looked the most obvious. So I zoomed in and I zoomed in and I thought, well, hello, look at this. Look at this. Extremely, completely equidistant from both walls of the channel. Same kind of thing. What could this be? So I zoomed in and we got this. So here's our little ball, and I decided to zoom in and here we go. Zoom in, zoom in. I thought, look at this. Look at all this structure around here, and this is completely different. And guess what? It's right in the center of this channel. Exactly in the center of this channel. So if this is the magnetic core of a micro ball lightning, and this is the field effect of it, you can see the scale. So the actual micro core, we'll look at the scale in a second, but this is 1 millimeter across this channel, and it's 500, half a millimeter either side. This is the sphere that it's producing of influence, and this is the ball in the center. Okay, Dan, you've not seen anything yet. I've got a punchline and it's coming right now, and this is going to absolutely melt your brain. We are seeing the same effect all over. And bear in mind what I said on Saturday. It was recorded on Saturday, and for the first time I saw this yesterday. I recorded what I said on Saturday, and then it was rebroadcast last night. But during the day on Monday, this is what I saw for the first time. I saw this, right? But this is very, very smooth. And this is not. These things are very different. So what is this? Well, as I showed you earlier, I'm not happy with seeing things that size. Prepare for it. This is absolutely friggin' awesome. Boom! Is that not so awesome? You want to see contrast? Look at the contrast here. This, my friends, looks a little like the thing we've seen pretty much everywhere else. This, my friends, looks like a very, very smooth, iron-rich, iron on oxygen, almost certainly, rich, crenellated sphere. Yes. And you know what? There isn't any thermite anywhere near this. No thermite, nowhere near. Not at all. No thermite at all. Nowhere near this. At all. Anywhere. It's brass and electricity. Brass and electricity. No thermite anywhere at all. We're going to see what it is in a second. I just wanted to show you the glorious circumference with its extreme levels of fidelity. This is a thing of great beauty. This, my friends, is in my opinion, without a shadow of a doubt, the magnetic core of a ball lightning-like structure. The magnetic core of a ball lightning-like structure. And is this either this point here where you've got the triple point, yeah, or is this dark little ring here the pole? I think one or the other is the pole, yeah. Maybe these 2 points here, I don't know. One or the other. Anyway, let's have a look at it. Absolutely, completely different to its surroundings, and 100% oriented into the center of this channel. Now, this may be because this one died, and it was kind of like its field structure oriented it to die at this particular place. And we'll see what I mean by saying that in a minute. But we already have one that was in other systems that we started out this presentation with. So let's find out what we are looking at here. Why not? Let me find it here. And it's not that. This is produced in an ultra experiment. And this is an iron and oxygen rich structure. And it's not as perfect. And you can notice there's a bit of a skin on this, and there's a bit of a skin on this, there's a bit of a skin on this, and there's a bit of a skin on this. This is in water with aluminium and ultrasonics. This is in brass with some residual gases and electric discharge. Yeah? And if we go back here, what I was showing you from a ball lightning that struck in Hessdalen, which is formed in the air. It's not formed by a lightning strike. That's why this is important. It's formed in the air. We have a structure. Where is it? Yeah, not that one. This one. Does that look like that? Does it? Look at the scale. 10 micron. Look at the scale of this. In fact, I'll get them to roughly the same size. Yeah? 10 micron, 10 micron. These things are almost identical scales. Almost identical scales. Okay? Even the size of the crenellations are pretty much the same between the two. The one from the natural ball lightning is a little bit more rough and ready. It might have been their scanning electron microscope, but the one from Henk's VEGA experiment is an absolutely near on perfect, as you could possibly imagine it, structure. So we're going to get the SEM here. If my machine doesn't fall over, just using a basic switch between two different tables in Excel. Okay, so first off, we've scaled it. So it's 27.3 micrometers. And spectrum 40 is the structure surrounding it. So let's see what the substrate is. Spectrum 40 is sulfur 0.13, so that's really not worth talking about. Iron 0.99, not really worth talking about. Oxygen, whatever. It's mainly copper and zinc. Copper and zinc. Yeah, it's mainly brass. This is brass. Okay, this is brass with the effect of ball lightning on it, in my view. I don't know if anyone's seen, but there's another smaller one down here, but we won't talk about that because you know, this ends up looking like that structure that we have been talking about recently. But anyway, there's a smaller one down here. So what is Spectrum 39? Spectrum 39 is, oh my god, look at this. Atomic percent, it is 30.59% Fe, and oxygen 62.84. This is, at least at the point that it's been analysed, it's FeO2. But it also has manganese in it. It has manganese in it, doesn't it? Well, who else was talking about the amazing circumstance that it has manganese in it? Oh, really? I wonder who was talking about that. Anyway, we won't go into that. But look, basically, copper and zinc are pretty much non-existent. They might, where I did the sampling on there, it might have caught up these flecks of contamination on here. So there may actually be no copper or zinc in there. And it might just be a trace of carbon and just iron and oxygen, and that's it. And that, my friends, we have proved, I believe, that ball lightning does have a magnetic core, and that magnetic core will present itself ultimately as iron and oxygen. Oxygen, I believe, is absolutely critical for forming these in the air. And I said that you've got nitrogen. Two 14 nitrogens go to silicon 28. Two silicon 28s go to what do you call it? Iron 54, I guess. You can get there quite quick from the nitrogen. You can also get there by fusing carbon and oxygen, because they're either side of nitrogen. So two carbons and oxygens, and two carbon and oxygen, two of each carbon and oxygen. You can get to iron. You might have to lose a helium or whatever. You can. The oxygen, though, is the anchor. It's the anchor, and this is, I believe, and I've said quite a few times now, that I believe that the oxygen, from my Russian presentation last year, that the oxygen is key in Brown's gas and in lightning generally, because it aggregates the magnetic monopoles. Roitskev suggested this in his 2006 paper, et al., about the effect above Chernobyl. The monopoles were collecting, and he says in the gases, but he does say that it was oxygen in the pipe. So I think oxygen is absolutely key because of its fairly unique nature, with all of the other elements anywhere near it. And so I believe that this underpins what happens in the ultra experiments, what happens in any form of HHO, Brown's gas, Amarza gas, what happens in natural ball lightning in the sky, and that you rapidly, through coherence, end up by producing a magnetic core, and the magnetic core leads to the formation of microball lightning and ball lightning, and this ends up by producing coherent matter, and the coherent matter will then eat and transmute whatever you like into whatever you like, depending on what kind of material you're starting with and the level at which you push it. So you will get these structures forming, and I think we're pretty much getting to the point where it's an absolutely categorical, this works and it works like that. And so there's someone asking a question about Mr. Jones, and I think that I think probably it was, we know people are going to find stuff in ash from Lena processes, and we need to come up with some excuse as to why it's something else. Or maybe he just didn't know, and he was genuinely being honest and got given a sample and thought, oh, look what this has got in it. And it just is a coincidence that he worked for whoever. But, you know, a electromagnetic system will produce microball lightning. It will produce these spheres. The spheres are the magnetic core, in my view, of the monopole and monopole cluster type structures. they will lead to consumption of matter and transmutation of matter. And as we showed with this one on the outside, in this case, it could be that the monopole is inside here, and this is attracting the copper, but I believe that there are smaller monopoles forming, and I believe that these triangles are a tell of the overall process. So if we go into this one, we can see triangles in other places, and it's a very specific shape. Of course, if they're oriented into the material, then they will present slightly differently. If I can zoom into this, so you can see a triangle here, triangle here, triangle here, triangle here. If we go over here, you've got the triangle here, a different angle triangle. Here's one of the triangles here. Here. And then if you get them at so you got the triangle here, this triangle here, and you got the triangle here, but this is the right kind of shape. You've got a triangle and it's got a little dip in here. It might just be where something grew, but anyway. In fact, even on the material around it, like for instance over here, so you can see here we got the triangle here. Now, one might argue this is where some crystals are coming together and they would naturally form a triangle, but that doesn't account for what I'm showing you in, where is it, triangles and spirals. I might need to go here. Or is it in here? I don't know. Give me a second. I'm getting there. That I started the presentation with here, and that I'm saying that this structure that was given to me by the universe with the magnetic core here, and the triangle is here, and in fact the actual symbol of remote view, this structure here, is from the Lion reactor, and this is the cone, and this is the vortex is going around here, and this is the magnetic core, which has a field of influence in here. But this is actually one of the Lion pore tracks, and we're going to see this in other presentations coming up, particularly with reference to things. At least one artifact in Iran, but this is the same triangle creating the monopole and causing the tearing of this iron rod. This is on I think this is from 2000, or this might be the 1980s, but I think it's 2007. This is 2007, and this is 2017. The same triangles in the Lion fused quartz, where it broke the fused quartz apart. So these are triangles appearing in the center of a piece of silicon dioxide, right? Okay, material is removed from the center of a piece of silicon dioxide. This thing here, if you actually look at it, I actually got the video here in my Sochi presentation from 2018. I go to it. Let me just kill that. It's probably going to give an advert here. So yes, this particular material was cut in half, and this shape was inside the material, and so it formed inside the material, and so we've got it in aluminium, iron, silicon dioxide, and here it's in copper and zinc, but mostly copper. This is the same triangles forming. And so I kind of see this whole thing. You might have the itonic clusters making the shells, but it's kind of like a swirling amount of monopoles. And actually, when you see, the Russians have done some x-rays of the birdies, and inside the birdies, they have a lot of things moving around. You can actually look at some substructure, and it might be that they are little monopoles that are forming the big monopole. So it's a fractal structure in its own right. And so, you know, there we go. It's a real pleasure to be able to share this with you. If you've got any questions, I'm going to show the money shot. So the first money shot, I would say, is our first Evo, which we saw, and it was this one. And we saw it like this, which looked much like Shoulder's Evo in his documentation, but when we look at it much closer, we see that it is iron and oxygen rich, and that in this case it clearly has a pole structure on it, and it has these scales. But this one is this is a 2 micron scale, so it's 2, 4, 6, 8, I don't know, definitely not more than 10, I don't think, microns in diameter. And then we went to look at this one, which happened to be in the dead center of a channel. And by the way, I think this is in the center because it died at that point. I think it probably was in, because this is between two plates, the ball lightning actually was in the center of the two plates at the time it died, and then when it died, the iron just fell down into, like, under gravity to the point it is here. I say that because if you actually look at this, there is an absolutely identical one, which I missed when I did the microscopy yesterday. Identical size over here. Okay, absolutely identical. I can tell you that this is another micro ball lightning core as far as I'm concerned. Here's the one that we've been looking at over here, and here is the one over here. Okay, and I think again in this case it died and fell there. This one fell here because when it died it just fell in the dead center. Maybe the field structure on this was already decayed by the time it came here, or maybe it was influenced by this one. I don't know. Now, I would like to spend a lot more time on this sample and just looking up some of the channels. So this is the bulk channel here where we first saw the structure, if I can go to it. So here, so that's sorry, that is the one we're looking at here. But I see there's one probably here. And in the center of the center here of this end of this channel, there is one probably here as well. So it might be that the ball lightning organizes itself, and that might account for the shape of these channels. Yeah, you got one here, and that's more of a ball. It's like the ball is here, and there's another one here, and that kind of that's influenced by maybe something that was over here, and there's another one here. And so when you look at those videos of them wetting together that we shared on in remote view, you can imagine something similar going on with the electron condensates in the channels. So where's a good example? Yeah, somewhere here. No, not there. Down here, maybe. Maybe here. Yeah, so you can imagine, like, now the question is, do these actually have a magnetic core to them as they're moving around, or is it something that has no dimension, and only when it gets to a certain scale, because these are 1 millimeter across, so these might be 1 millimeter across, but the channel here is, and this is 2 millimeters, so the channel is at least 1 millimeter across when we look at this. So can they move around because of the field structure? But inside here, there is a magnetic core, but the magnetic core has got no electrons. The electrons are all in some sort of coherent thing that's at a much greater distance from the magnetic core. So there's a lot of questions to still be answered, of course. But I think we can safely conclude that you can't get away from ion crenellated spheres when you're talking about a cold fusion process, a HHO process, and so forth, because you're and an ultrasound in water process. And I think that is just absolutely spectacular. And as I say, there's two within a very short distance of each other, which are exactly the same size. So it's not a one-off. And I believe that you would find lots of them on the same sample if I had more time. There's another little one down here, which is more of the order of the first one that we found. But this one is almost identical scale-wise to the one found at Hessdalen. No, you can't see them with optical at all. What I'm going to do is I'm going to look at the 50 megapixel images, and I'll see if I can identify this part on it. I think the FeO2 is forming the enhanced magnetic field, and I think these balls are very magnetic. And I think the first one that we showed, this one is intensely magnetic, and I think that it's still in a semi-live state, and that's why it's able to suck in the electrons that it is. But it is smaller. Like I say, this is. Is it smaller? I don't know. Is it bigger? It's bigger. 2 microns. It's what did I say? 8 or 9 microns. What's the other one? Maybe it's bigger. This one is. No, this is 20 something microns across, isn't it? What I measure it as in the Excel. It's 27.3 microns. So this is a much bigger structure. Okay, and it kind of stands to reason that the one at the end of the flood chain would be smaller. The floodplain, rather, as I call it, the floodplain of the coherent electrons, the fluidized electrons. Yeah, so these ones are the same size. Okay, so I'll take your questions, but that's it. It's all the same thing. No surprise there. Right. Okay, WP for truth. Hey Bob, two out of phase lightning balls, or maybe two. Always have to be close to one another. Well, I think what I'm suggesting maybe here is that this is like the lantern that we saw. You get a small ball and a big ball in this relationship. And so, I'd have to find out with more detail what that is. Also, it'd be interesting to see if we could zoom into this ball and see it with some more detail as to whether that is a crenellated sphere, because that's about 3 microns across, this particular one. Yes, David. Basically, iron and O2 are very high magnetic susceptibility. In fact, the colder oxygen O2 gets, it has higher and higher magnetic susceptibility. So, did you manage to get a reference composition on an unaffected portion of the brass? I might have done actually elsewhere. That can be done at any time, to be honest. The unaffected areas are just pretty flat, so maybe we can look at this, which is largely unaffected. I think maybe I look at something outside of this area. So there's some areas up here that are not so affected. So well, they've all had a little bit of a go at, but nothing like what you see there. So let's. I think I've got something that I can look at. I call it tongue. There we go. And I've got line data on the tongue. And so, oh yeah, this is interesting. It has a very large amount of beryllium. which I don't particularly want to be touching, to be honest. Yeah, look at the... Go to the line scan here. Line scan, not lion scan, line scan. Oh, you wait until I show you what happened in the Ultra experiment. Oh dear, here we go. Jackanory time. Page layout. This is our view. Oh, normal. Just give me normal. Okay. So, no, I need to put the break in, don't I? This is not graphed. It's just raw data. So there's only a graph for sodium, bizarrely. This is what I was given. So I need to put in a thing here. Okay. No. Okay. So look at the copper and the zinc column are here. Oh, I'll put on the copper column. And this is outside of the beam of the EDS, so it couldn't see this. So it's mostly copper and zinc and whatever this column is here. I don't know. I have to look at that later. But yeah, the cumulative thing was here for the entire line scan. I know that as it went across the boundary here, there was an intense spike of carbon. So on the inside of the double there, it's synthesizing carbon, but I think we already know that. Yeah, so oxygen, beryllium, carbon, sodium. Yeah, so the zinc can boil out and then be redeposited. So there's a lot of that going on, I should imagine. So it's a vapor deposition. And so you end up with seeing a lot of zinc on the surface, and it kind of skews the ratio. But essentially this is brass with some oxide, but bizarrely it's got all this beryllium. I'm not convinced on the beryllium. I would need to, yeah, you see, no, so forget the beryllium. It's confused about something. It's not actually, it's saying it sees something of this level. So I would expect actually the beryllium, for whatever reason, is actually copper. And this is basically brass. So it's seeing brass. And that's it. That's essentially the material starting with is should be brass. And it looks like it probably is. So that's the best answer I can give you at this time. No, I don't think it's beryllium. I think it's yeah. I'm going to go back to our lovely picture. Natural ball lightning, Henk VEGA experiment. Natural ball lightning, Henk VEGA experiment. Pretty much identical scales. Pretty much identical levels of crenellation and size. There we go. This is not a micrometeorite. This is not a micrometeorite, although quite likely meteorites, as we saw with the diamond shelled structure in the Chelyabinsk being very, very similar to the HHO on carbon in the Slobodan-Stankovic experiment. I would expect them to also produce structures like this, but given the fact that we've shown it in cavitation as well, it's almost like where you get coherence, you're going to get this kind of thing going on. I do not think it was a coincidence that the Air Force commissioned a report in October 2001 to find out anyone in the world that knew anything about ball lightning and related technology. I do not think that that was a coincidence. Yes, that's right, David. That's my point. O2 is cold if it's in the condensed matter state. Yes. So about drop out of the balls when it's something good. I think you'll see that with cavitation that we should be able to hone it with a bit of effort and cycling and learn what needs to be done. And so I think my next presentation this week, which I might do, I don't know, what is it? When it's Tuesday evening for you guys. I might do it on Thursday, or I might hold it to the end of the week. I've got so much to share with you guys. So, but yeah, I think with ultra experiments, that is really the simple way to go. And I think there's no excuse for any curious scientist in the world not to try that experiment. It's basically cost free, it's effort free, it's brain dead to do, like I say, I said to Martina, I would like to bring in the apparatus when your boss is here, and he can bring the distilled water, and he can bring the cleaning, and he can bring the aluminium. We'll do the experiment. You can look at the before, and you can look at the after, and we'll see if we can connect any magnetic crenellated iron oxide rich spheres. Steve Windish, if you want to go and find out about this experiment, go and have a look at the many postings both on the MFMP YouTube channel and on remoteview.icu under the banner VEGA. So this is and specifically the Vega Valley. So you can see spectacularly detailed 3D and 2D images of the Vega Valley. And animated, and you can see in the course of this video when you review it very extremely detailed images which and the location of the structures logically making sense for something that has a field structure to it, interacting with the electron beams from the electron microscope in a way that shows that it interacts with electrons, and the fact that it is iron and oxygen rich, and in the case of this one also has manganese in it, and therefore specially nice. And no thermite anywhere at all. No thermite, no jet fuel anywhere in this experiment, none at all. Cool, Dave. I look forward to seeing it. Yes. So when I do my presentation on whenever on Ultra, the next one, I will make an extended argument to what I said at ICCF 22 in September 2019. Where I said the Mars vibrator plate can make every element in the periodic table, and by the way, water running down a stream does this also. And in fact, there are ancient artifacts where people they would put water in, and they had little things on the top, and they would rub their hands on it, and they would form standing waves. And I believe that was to make the water better for you. because vibrating it in there, I believe, as we've shown in the ultra experiments, the cohering structures can form in the water itself. They don't necessarily need a surface to form on. The free surface of the water itself is something that can form on, and also the surface of between the container. But regardless, I think this can form coherence, and the coherence can form synthesis of nascent elements. And if you're starting with water, you tend to produce them. And I am telling you now, there is something you can do, and I've already told you what it is. And if you go and look in the history, there is already some advice as to what you should do, or evidence that would support why you should do things. But specifically, I will talk about how you could accentuate this effect with the learning that I've showed you today and in the past. And it explains some of the things that have been done with alchemy in the past. And so I thank the person that sent me the video. I can't remember who it was, and maybe they can send the link to me again so I don't have to find it, of these vibrating things. Okay, so I'm going to say goodnight. I think pretty much we've closed the book on the iron crenellated microspheres. For me, it was an absolutely amazing, amazing circumstance that I could present what I presented after years and years of research on Saturday, and on Monday, before the restream, have observed it, and obviously it's in many places in the Vega Valley, something is at work with the work that we are doing together. Some force greater than ourselves is at work in making things happen at the time that they're happening. And I thank all the people that have supported the work so far. I especially thank Charles and recent donation from a chap who likes to keep himself private in the US. So thank you for that. That's going to help us on the US side. And we are going to step up with some learn from the nitric oxide from the paper in 1993, or submitted in 1993, about what ball lightning is trying to tell us in fusion technology, and also HF4. These have their own risks, but we're going to get those and see if that accentuates the thing. But I think this is simple enough. I think we've shown that in an electric discharge system you will create these things, and in a ultrasonic cavitation thing you will create these things, and in an HHO system you will create these things. So, hey Bob, sphere's magnetic core, electrostatic field surrounding in opposite spin direction. I think if they are one or other pole. I'll talk about that when I refer to ultra experiment. I think it become quite clear. These resonant synchronization into coherent matter seem more likely to cause beta decay reversal than any idea of magnetic monopole. The magnetic monopoles exist. Whether they're at play, I don't know. But they look like they're at play. But they definitely exist. Yes, okay, so yeah, you're going to see very close with the SEM work that was done. And I think it's going to be very, very clear that the figure of eights, the standing wave structures, are doing the work. And, it's a hydrodynamic version of what I believe you're seeing, a magnetohydrodynamic structure here. Essentially, it plays to the same end goal, to form coherent matter, in my view. Okay, so thank you very much. I will see you in the next stream. Have a great evening. Arrivederci. Buenas noches. And work together. Be coherent. It's the way forward. See ya.